Hey guys, welcome back to another installment of electrochemistry. So here's electrochemistry, and I thought I would just do an example of maybe an electrolysis of a metal in water. So that one might come up, and that's kind of an interesting one. So let's say that we have the water right here. So we've got H2O, and let's say that in this H2O is copper ions. So we got copper ions in there, and we're going to go ahead and do some electrolysis. So we're going to have a couple of electrodes in here, right? And we're going to put some current in between those. Okay, so let's say what happens is we put 4 amps of current through there for 30 minutes, okay? And what happens is that this ionized copper, which is, let's say that this is 3 molar copper ions, right, in solution. Let's say I have a total of 500 milliliters, okay. Let's see, what other information do we need? Let's say that the copper goes from its ionic form into solid copper, and oxygen gas is produced. Okay, just oxygen gas is produced. So let's figure out, first of all, what are my half reactions. So if copper is going from an ionic form to a solid form, if it's a 2+, it's going to have to get 2 negative electrons to go over to the copper in the solid form. And so that's going to be, when you have the electrons here on the reactant side, that's going to be a reduction, right? So there's my reduction because I'm gaining electrons. Remember, Leo the lion says gur, so this is my gur. Gain of electrons is reduction. So copper is gaining electrons clearly. And so what's losing the electrons? So in this situation, we have water is the only other thing that we're working with here. So water must be losing electrons. So for water to lose electrons, oxygen is not likely to lose any electrons. So we said that we'd produce oxygen gas. So oxygen gas is going to come out. And so what does that leave? Well, that leaves the hydrogen. So if the hydrogen loses electrons, you know, H2 has an oxidation state of 0. So if we go to H+, that's where our electrons are coming from. Okay, so we have H+, and then that's going to be plus an electron. We do need to balance this. We got 2 oxygens here, so we have to put 2 oxygens here. That makes 4 hydrogens here, which is going to release 4 electrons. So here's the half reaction for my oxygen, and then this is going to be oxidation. Okay, so let's label these anodes and cathodes. So which one's going to be the anode and which one's going to be the cathode? So let's say that this one is where the copper builds up, right? So the copper is going into this one. Well, this is reduction, and so if you remember your thing, red cat. So reduction happens at the cathode, and this one's going to be anox. So reduction is happening here. So this one, we can label this the cathode. And then this one right here is going to be the anode, because anox, okay? The anode is where oxidation occurs. So now we know the oxidation, now we know the reduction. What else can we figure out about this? Well, what if we wanted to figure out how much oxygen gas is going to be produced in this whole scenario? So that's not hard to figure out. But what we really need to know, and one of the easiest ways to do some of these electrochem things, if you're trying to sort of do a bit of stoichiometry and figure out how much of this and that, is to figure out moles of electrons. So moles of electrons equals the total amount of coulombs, right, divided by Faraday's number. And Faraday's number is 96,500. So what we can do is that coulombs always equals your amps times your seconds, right? Okay, so we know both of those bits of information. So our amps times our seconds. Our amps is 4. So let's go back up here. So we got 4 amps, and 30 minutes. 30 times 60 is 1800. So we have 4 times 1800. So my moles of electrons is going to be, I got to figure out my coulombs. So 4 times 1800 is, let's see, 7200. So 7200 coulombs divided by Faraday's number, which is always 96,500. And so that's going to give me moles of electrons. So my total number of moles of electrons, if I divide this out, is 0.075 moles of electrons. All right, so let's look back at I wanted to figure out how much oxygen gas was produced. And let's say that we collect this oxygen gas at STP. That'll make it a little bit easier. We won't bring any of the other gas laws into it at this time, but you could. So let's say that my oxygen gas was collected at STP. So if my oxygen gas is collected at STP, I have a total of 0.075 moles of electrons. But you can see for every 1 mole of oxygen gas, 4 moles of electrons are created. So this number is going to be 4 times too big to figure out my moles of oxygen. So if I divide that by 4, I'm going to get my moles of oxygen. So let's go ahead and do that. That's 0.0186 moles of O2. All right, now that I know my moles of O2, if I collected this at STP, all I got to do is multiply this by 22.4 liters. And then I'll figure out my total number of liters of oxygen gas. And so let's go ahead and do that. I have 0.418 liters of O2. Okay? So that was pretty simple, figuring out how much O2. So could we also figure out how much solid copper was produced? All right, well, the solid copper, you see that for every mole of electrons that passes through here, it takes 2 moles to make 1 mole of solid copper. So if we had a total of 0.075 moles that went through here, so 0.075 moles of electrons, right? For every 2 moles of electrons, we had 1 mole of solid copper. So if we divide that by 2, we'll get the total moles of solid copper. So divide that by 2 gives me 0.0375 moles of solid copper. Multiply that by the molar mass of copper, which is 63.546, and we get 2.38 grams of solid copper. All right, so that's how much solid copper was produced. So you can see you can do a lot when you figure out the moles of electrons. And moles of electrons is really easy to figure out with electrolytic cells. If they tell you amps and they tell you minutes, it's a piece of cake. And then if you know your half reactions, you can easily solve a ton of stuff. What about pH? We notice from this right here that if we are going to be creating, let me kind of rewrite that so it's clear. This is +4 hydrogen ions. So if we're taking the electrons from the hydrogen, then we're creating all these hydrogen ions in solution. And that's going to create a really, really high pH. So let's take a look at that for a second. So for every 4 hydrogens, there's 4 electrons. So it's a 1-to-1 ratio on the amount of moles of electrons as it is moles of hydrogens. So that means that there's 0.075 moles of hydrogen ions created, right? And so what we need to know then to solve for pH is we need to know the molarity of these hydrogen ions. So the molarity is going to be the amount of moles divided by the amount of liters. So we've got 0.5 liters up here. It says 500 milliliters, so we got 0.5 liters. So we divide that out, and let's see, divide that out, and I get 0.15 molar solution of hydrogen. That's a really strong solution of hydrogen ions. If I take the negative log of any concentration of hydrogen ions, this is my hydrogen ion concentration, right? If I take the negative log of that, it's going to give me the pH, because the negative log of the hydrogen ion concentration equals the pH. So take the negative log of that, and my pH equals 0.82. Whew, that is very acidic. All right, so we probably won't want to run that one anymore. I don't even know if it's possible to get to that acidity. But anyways, that's kind of what the example did, and I kind of made up those numbers anyways. So I hope this helps. This shows you kind of a simple way to do electrolytic cells. Remember, electrolytic cells is when the electricity is flowing into it. So this is where you can take things in their opposite direction.